Hello everyone, it's November the 2nd. It's very surprising to see we have a hard question today. Let's take a look. Beginning of the month, right? It's like, I remember beginning of October, it's also difficult. Or is it? Or the beginning of September? Alright, let's see. Have I done this before? I have. I've done it before. And one shot. Huh. Okay, let's see. Given an m by n integer array, where grid ij could be 1 representing the starting square, there's exactly 1, 2 representing the n square, exactly 1, 0 representing the empty square, so we can walk, minus 1 representing the obstacle, so we cannot walk. Return the number of 4 directional walks from the starting square to the ending square that walk over every non-obstacle square exactly once. So we have to walk, hold on, 4 directional walks from the starting square to the ending square that walk over every non-obstacle. So it's like you have to be, no, how do you do this? We have 2 paths, 0, 0, 0, 1, 0, 2, 0, 3, 0, 1, 0, 3, 1, 3, 1, 2, 1, 1, 1, 0, 2, 0, 2, 1. Huh? Oh, 2, 2. Oh, this is the end. This is the end. This is okay. So this is the end. So or that's it. 2 paths. So here we have 4 paths. Cannot do this way. Well, we can hit this with this and this, right? So basically, just how many paths? I seem to. So this is 2 paths. Oh wait, no, this is no path. Maybe it's DP. I mean, given that I answered in one shot, and this one has a very high pass rate, which means this is not actually that difficult. Alright, I think this is atypical. Let's see this one. Alright, so this is the starting point, this is the end point. So we're going to see how many paths, unique paths. So to get to the last spot, we can either go here and here. So it's the number of unique paths ending here, right? And number of unique paths ending here. So we're going to look at this and this. So about this, the unique path ending here is the unique path ending in this one and this one. So we need to look for this one and this one. And this is the same, this one and this one, right? So if I get that diagonal and the unique path is here, it's going to be this one, it's going to be this one, this one, this one, this one. So we start from here, right? So unique path for this ending in this is 1. This is 1 as well. It's the start, this is the end, right? And their unique path that end in this spot is going to be 1 because it can only go from here. Oh, it can go from here as well. Hold on. Yeah, it can go from all 4 directions. Let me think again. Unique path that can end in this spot. Right, if I want to end in this spot from here, it can be 4 direction walks from the starting square to the ending square, from the starting square to the ending square, right? And we have to cover every single obstacles. And M&N, every single, not every single obstacle, so every single non-obstacle square exactly once. let's say if I have one, right, one starting point, and then there is exactly one starting cell and a one ending cell. So at least they gotta be, well, the starting point is the end point. That will be what, 0? That'll be, okay, I don't know. But anyway, so let's say we have 2, right? This is starting, this is the ending, that is one path. Okay, that's one path. What if I have 4? Right, if the end point is here, how many can we get to this one? Well, to get to this one, we need to go through every single one. Right, every single one. What's the requirement of go through every single one? Well, to go through every single one, that's actually not possible because in this, right, there's no path or walk away. Look at the starting and ending square can be anywhere in the grid. There's no path that walks over every empty square. We need to walk past every empty square. We need to walk past every empty square. So the previous analysis is not right, because if I enter here, that means we have to traverse everything to go here. We have to go past every single one. Mamma mia, what's the inside? We know that if it's here, then it's a no-go. Right? I can't. But if it's here, then I have at least one. Yeah, at least one. And if I can put the end like in here, right? I can put it anywhere. How many paths are there to cover the entire thing? So like if I start walking by walking here to the right, right? Like I can go, oh, there are a lot of different ways to, So like if it's, the flag is here, I have a path. If the flag is here, I have a path. But if the flag is, so if it's a 2x2, right? The 2x2 flag is here, I have a path. If the flag is here, I have a path. But if the flag is here, I don't have a path because I cannot access this spot. Okay, so if it's, let's say 2x2, we have 2 paths. Can we extrapolate from that? What if a 3x3? Like a, no, like 2x3. Well, 2x3 do have, if it's at the start and end, do have it. And I can say, what can I say? If a starting position is somewhere, like it's right next to it, and then I have one path to it. So if starting position is here, I have this path. Starting position is here, I have this path, right? Or directly down. So I just need to know how many passes to get to here. Okay, how many passes to get to here? So if we could, and then to get to here, I have to go through the entire thing. Just not likely. Let me think again. If it's a 2x2, and then if it's 2 by 2 with any destination, if it's 2 by 2, I can have the starting point in here and here. Like the diagonal wise, I can always reach it. So in this case, it's here, right? So let's say I want to reach this position and this position, because these two positions guarantees that I can go down here. This thing I can go down here, right? Okay, if that's the case, and I cannot, if I reach this position, if everything else is done, I reach this position, then there's no way. Right? If I'm here, unless I hit this one already, and then I'm actually here, right? So if this 2 by 2 has never been hit before, right, and I'm here, then I'm done. I cannot do it. So I have to hit here or here. The question is, can I reach this position and this position from the start, going through every single one? No, I don't like this way of thinking. Let's change it up. This position I can go, right? In this position I can go. This position I can go like this, but this one is not encountered. How do we solve this? I mean, we can say in this, if we want to simplify it into a, so like go this and come in here, right? So this is the same problem as a 3 by 2 problem. And the 3 by 2 problem, I can come here, right? And that it's solved. Okay, so let's say, can I reach this position? Yes, I can reach this position. And I want to reach this position. All right, that's one way. Or I can reach this position. Right, if I reach this position, I can reach this position as well. I don't know. I was able to solve it last time. I have no clue whatsoever this time. Number of 4 directional walks from the starting to the ending. Now walk over every non-obstacle square exactly once. Gosh, exactly once. Okay, there's another way. We just DFS this thing. Alright, we just DFS this thing because we know the total steps. Alright, we know the total steps. We just DFS this thing, and then it has to be the same number of steps. How about that? Because it's only 20 by 20. So if we DFS, this might work. We just DFS and then DFS with backtracking. Alright, so we go, whatever, and then we hit it, but if it's not good, we keep going, and then if we hit more than the required, then we know it's no good. It has to be hitting the required. Maybe that is why it was successful last time. Yeah, I was trying to analyze this. I don't see any way I can analyze it. Alright, I'm gonna go DFS with backtracking. So for sure, first thing we need to count how many steps is required. Right, so go this. So I have a grid. I need to check. So the steps required. It's just the number of the number of zeros, right? So we're going to count the number of zeros. So steps for 0, and then we say for row in grid, row.count 0, right? Steps plus equal row.count 0. I think this is true, right? I'm not sure actually. I think let's say 0, 1, 2, 0, 0. I can call a.count 0. Exactly. So I can count it. So I know the total steps. Then dfs, we have ij. Right, ij is position, and we need another value, self.res. Right, that's the count of total number of steps. No, total number of valid path, and we also have path. Path is going to be. We don't have to have a path. We can just change the value. Yeah, we can just change the value. So we don't need a path. We just change the value. Okay. But we need to know step, right? Now I'm going to change this. This should be total steps. Right? Total steps. Oh, is it? 1, 2, 3, 4, 5, 6, 7, 8, 9. I mean, the last step to reach, because every time we go, steps plus equal 1. So where do we step plus equal 1? Step plus equal 1, and then pass in. So when I add this, I already add the path. I already add the step. So I already add the step, right? So the total step should be 1. So we count the number of zeros, so like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 10 steps to reach this position. So as total steps, and then steps is something we're just going to increment along the way. So we're going to increment a step and then go to there, right? So now I'm at ij. I'm going to check if steps is if steps equals to total steps and grid ij, right? Grid ij. So we have -1, 0. 2 is the ending. So if this one is equal to 2, right? So we take the total number of steps and then this, so that's good. So it's a self.res plus equal 1. Alright? And then we just return. Else, elif steps is equal to let's actually do this. If this, then this, else, which means the grid is not equal to, we enter a grid that is not, right? Then we shall return. Yeah, we just return. Yeah, we just return. That doesn't matter. Doesn't matter. We simply return. So if this, hold on. If this, we do this. Otherwise, we simply don't keep going, right? Simply don't keep going. I think it's fine. So we can just say, and we simply do this, and don't keep going. Otherwise, if this is smaller than total steps, which means if it's equal and this is not, we just ignore it. Or this is smaller, right? If this is smaller than total steps, that's when we go. So for ninj in, so I plus 1j, right? I minus 1j, ij plus 1, and I j minus 1, right? And then we say if 0 smaller, or we need, like usual, mn equals len grid 0. Alright, so here say 0 smaller equal to ni smaller to m, and 0 smaller equal to nj smaller equal to n, and the thing we have not seen before, so grid ninj is not equal to, so what value should you use? Let's use 3, right? If this is not equal to 3, so 3 is the sentinel that we have visited already. So if it's not equal to 3, then we say steps plus equal 1, right? And then we DFS and ing steps. Plus 1, look at this, neat. Right, so we DFS and blah blah blah. Once the DFS is done, right? Oh, where do we change? Now we're changing here. So grid ning, we change in here equals 3. So visited, right? Visited, and then we go there. And once we finish, right? Once this path is done, we want to go back and try it again. And then we turn it back to 0. Right, turn it back to 0. Actually, this has to equal to 0. Has to equal to 0. My bad. It has to be an unvisited, right? It has to be equal to 0. Then I visit. Oh, but we need to visit if it's 1 as well, or if it's 2 as well. So it's 0 or 2. Jesus. 0 or 2. If it's an ending square or someone we can walk. So which means this mod 2 is 0, right? Because I get 3 mod 2 is 1, 1 mod 2 is 1, minus 1 mod 2, whatever the value is, it's not going to be 0. So that's the one we're going to go, and then we're going to set it to this, and we're going to go, holy guacamole, what if it is the last value? Jeez, so we need, we need to have temp. Yeah, we need to get a temp value first, and then we're going to change it, and then we're going to change it back to temp. All right. Visited. We're going to go blah. So now we're going to go back, change it, and that's it. Anything else, we just going to ignore. So now we go DFS 0, 0, and steps. Start from 0. 0 steps. And first one will be the 1 step. And we're going to return self.res. Alright, let's see. I think this should be right because it's, how should I call it? It's very small, right? It's 20 by 20. It's very small, so whatever brute force will work. This one's 4. This one is 0. Right? And I can actually add one more test case. 1 and 0, 2, right? Which means we put the ending here, so that has to be 1. This will be 1. I might as well add another one, which both is on the left side, right? So 1, 0, 2, 0, that should be 1 as well. So we're going to have grid and unique path grid, run it. The result is 0. That is not correct. Okay, so we have some issues, which is fine. Let's debug it, see where we got it wrong. Total steps is how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Total steps should be 11. So first check, so let's print total steps, 11, okay, that is correct. And every time we go, so we start from, we start from 0, 0? We don't start from 0, 0. We start from, we need to find the starting position as well. Alright, this is not going to work then. So we hand to si sj equals 0, 0. We don't know. So for this, right? And I hate it. I have to go one by one to check. stupid. I might as well. For I in range M, j in range N, if grid ij is equal to 1, sij equals ij, if grid ij equals 0, then we do this, false equal 1. And then I'm going to start from sij. It's still not going to be right, but we at least solve this problem. Okay, so because I changed it to 3, that's why it's not registering. So we don't change it here. Mamma mia. Well, 2 is, I mean, we can just we say when we go is when it's divided by 2, right? Okay, so we can just do temp plus 1, right? Instead of doing this, we're going to go temp plus 1, which will make sure it's not an odd number becomes an even number. Not an even number become an odd number. And I don't care about 1 because that's where it is. So we're going to do 10 plus 1, which gives us the odd number. And here, that is going to be 2. No, that's actually going to be 3. Because if it's these, they will become 1. So this shall be right. So endpoint becomes 3. Right? Endpoint is 2 plus 1 equals 3. Just note it. Okay, so the rest. Yep. I think this one shall be right. It's an interesting question. 48 the first time. 68 the second time. Okay, what did I do last time? It's more than a year ago. Did I use something smarter? I got a limit, obstacles. I count minus 1. I count number of obstacles, so I count the number of squares. Find a starting point. Find an ending point. Just backtrack to search the map. So I search the map. Current path equals, I add into the path. Else is the path. Where did I define current path? Let's define current path here. And I say if this, and grid in 0. So the next grid is this. Current path. And then grid. I set to minus 2. And I backtrack. I set it back to 0 and I pop it. Yeah, it's the same idea, but I actually like this implementation better because I don't have to keep a current path. There's no need to keep a current path. I was using 2 techniques at the same time. I got a path and I got using the grid itself to indicate which one we visit, which one we have not. But we can just use a little bit trick here. But it's slower. 39 test cases. Maybe we have more test cases this time. It shouldn't be only 1 year. That's the same. 39 test cases. Oh, that's when it runs in nice. So it's the same idea, right? So this is the same algorithm as I did more than a year ago. Right? More than a year ago. Brute force it. We traverse the entire grid and see how many paths traverse the entire grid. No, we don't traverse first, we count. We count the required number of steps to reach the destination with all open cells traversed. Then we traverse the entire grid and see how many paths that reach the destination have the same number of steps as required. And that's basically it. Now this is slow, but since the grid size is 20 by 20 at most, it works. Yeah, it works. So this one is 6 milliseconds. What is the runtime? I think I had the same problem as before. Well, each spot we have 3 right to go. Each spot will have 3 to go. So the worst case scenario shall be mn 3 to the m times n. I think that's the runtime. Wait, hold on. So this one 3 times 3 times 3. Yeah, 3 to the mn. That's the runtime. I'm gonna go at 68 milliseconds. 62. Right, got 62 percent. Thank you. Okay. Yeah. Let's check back. Backtracking DFS. Brute force. Yeah, it's basically just brute force. Yeah, when I find empty, find number of empty, find x and y, if not, if this equals to this, we do this. Ah, that's the way to do it, we do -2, right? If it's larger than 0. Ah, that is, okay, I see. Yeah, same idea, but they use, oh, I know, it's because of this. You know what? Yeah, let's use -2. Yeah, let's use -2. Let's use -2, and this has to be either 0 or 2, right? And then we won't hit. But what if when we start with 1, we'll go back to 1 as well. Larger or equal to 0. Because we checked here. So if we go back to the start, it's fine. Okay. Larger or equal to, I'll just set to -2. And now we have to reset to 0, right? We reset to 0. We shouldn't reset to 0 because we also visit. Larger or equal to 2. Hold on. We reset it and then we set it here. We say it's larger or equal to 0, which means it's 0, 1 or 2, and then I'll set it to -2 and then visit it. But as I visit it, shouldn't that be I already changed it to -2. And to check if it's 2. Right? I change it to this, and I go to the next one. And if it's not larger than 0, now we don't go. If it is, if everything is fine, then I check if it's equal to 2. If it's not equal to 2, oh, I see. They avoid the problem by changing it. Nah, I don't like it. No, I like how I want to do it. But in this case, yeah, I am stuck because I simply cannot, right? I say I go with a place where it's logic equal to 0, so it's either 1, 0, or 2. But before I go, I will change it, and then I go, right? Another way to think about it is I'm at myself, right? I already entered, and then I change myself. Yeah, that's like a different way of thinking. Here is look before you go. That's the way I'm doing it. So when I'm entering ij, I already changed. See, that's the problem. I already changed. So I have to figure out a way to change myself to a value that I can detect. I mean, what should we do? Apparently, there's another right way to go. So, okay, so we go first, right? So that's the idea. We go first. If it's good, we go first. Now, once we enter myself, then I can check, right? I can check, and that's I check. After I check, I do this. Otherwise, I need to mark myself. Yeah, I mark myself here. Right? So we grid ij, and mark myself as -2 here. So mark as visited, and then I go around, and then right, and then I don't need this. I simply go. Right, I go because I already marked. And by the time I'm done, I change myself back to 0. And this is no good. Why is that? 2 is the destination, right? So I'll go. Sorry, it's J, right? I'll go. And total steps is good. So I'll change myself to -2. And then I look around. If it's good, I go. Right? I go to the next step. And it's fine. I can change it to 0. That's fine. I'll go to the next one, and I'll check. Why is this change doesn't work? Yeah, steps is less than, then I'll go. If the steps is more than, right? If I hit 1, steps is equal, and it's not equal to 2. Right? It's not equal to 2. If it's equal to the total steps, it won't be. So what happened is it's smaller and it's equal, but or I hit 2 already. I think it's because I hit and I changed the 2 already. I think it should be or, right? And then we're gonna say plus equal to steps equals this and, right? So we're gonna plus equal to this. There we go. Which means whichever is true, and I'm going to check it. And to check it, it has to be these, and both has to be true. I'm doing like a lot of repeated computation. I don't like it. Well, I do think the only thing we need to check is if it's equal to 2. Because it's guaranteed that I'm not going to go back. It's not going to, like, each cell will visit once. So the only thing happens is this. If it's this, then I just simply go to this. Yep. Yeah, I think this is the better one. Let's try this one. Well, because we don't have a mod, so this should be faster. I'm going to remove this. I'm pretty sure this one will be faster. Alright, let's see. Yep, okay, this is faster. Okay, 98. Actually, yeah, that's fine. Just say note to, what should I do? I should note the previous and the difference. Right. Update. The previous version only registers 62% ranking, which is due to the use of modulo. Right. Now we can avoid that by changing when grid cell is marked as visited. So instead of marking it before visiting it, we now visit it first and then mark it. This allows us to mark the value and mark the visited with -2 without having to worry about changing the value of the endpoint as well. Right. We simply examine the endpoint first, right? Examine the endpoint first, and then if examine the endpoint first. If the endpoint, right, has not been reached, then we mark the cell as visited. Yeah. So this way is better. So maybe this should be how we do moving on, right? DFS go directly for it, and the backtracking happens like at my current step. Yeah, I like how this one looks. All right. Well, I'm kind of lazy today. Let's end it right now. Yeah, this is not really a difficult question. That's why it has a lot of passing rate, like 70% passing rate. Anyway, I'll see you guys tomorrow. Adios.